Hello everyone, my name is Dr.Moustafa. I'm a postdoc in University of Science Malaysia, Physical Civil Engineering. I'm specialized in structural and earthquake engineering. Recently, I have been graduated from USM at 2021, March 2021. My PhD topic was about vulnerability index technique, and which is related to our work today, which is related to our modeling. And I use ETABS and a lot of finite element and software to finalize my PhD work. Today in this video, I'm going to explain the interface and brief introduction about ETABS and the information in this program. When you say ETABS is one of the CSI software, is one of the commonly used program for analysis, design of building, which is made actually for the purpose of design for building. You know, there's a lot of family from the CSI program, which come like for SAP 2000. I think you are familiar with SAP 2000. I don't know if you're familiar or not, but this is famous in the CSI softwares. Rivet structures, one of the famous also. Rivet also can be for architect, can be for structure, can be for mechanical, can be for electrical. So it's a big family in design in the engineering field. Between these CSI softwares, there will be a lot of interaction between each others. But for our interest will be only related for the structure design. Now, the idea using from ETABS is going to model a structure, right? So let me start with a brief description of brief information about the softwares. Let me say that the ETABS training session that we are going to cover within the 5 sessions. First, we can go for, let me put this one first. Let's put that, okay. First, we are going to import from AutoCAD to ETABS. Okay, then try to define the materials. Importing from AutoCAD to ETABS, usually you have an architect plan. If you have a project, you need to have an architect plan for the building, for the plan view, for the slab, for the floor systems, for the distribution of beams and columns. That's why usually the architect engineer have always conflict with the structural engineers, because sometimes the architect want the column in some place, in some position, particular position, and sometimes the structural engineer doesn't want this column to be here because of some structural analysis issues, safety issues, factor of safeties. So the first thing we should know how to import from AutoCAD to ETABS software. Later on, we will need to define the material. The material could be concrete, could be steel structure, could be timber, could be masonry, can be any type of material. You can define the software. After that, after defining material and assigning material, we are going to do the 3D model for the restructure, bringing this model from the realistic into modeling, brings this from AutoCAD stage to the 3D model stage. So after modeling, we are going to define the loads, which is vertical loading, which is related for the gravity load, dead load, live load, superimposed, plastering, tiles, etc. And the live load, which will be based on the standard codes. And horizontal load could be wind, could be earthquake, seismic, depends on the situation of the building, how it is designed, how it is in importance. analysis. After defining the load, we can see the analysis. We need to analyze the internal forces for the beams, for example. We need to see the major moment, the minor moment, the bending moment diagram, shear, negative moment, positive moment, and shear force, axial, okay, axial for the column. And we can check for the story drift and the sway based on the code requirement, check the stresses, design the vertical element, and finally we can make detailing, drawing how the rebars are distributed, and what else? Also, we can make bill of quantity. If we have time, we can make bill of quantity. Okay, but the basic modeling and analysis concept. This is can be like yeah, it can be the building structural physical system. This is like a physical system starting from here's a building structure. The building structure usually splitted between frame and shear walls. This are the lateral loading resisting system, and the horizontal element, which is denoted or known by the floor diaphragm. So we have two elements vertically, which is related for the lateral load resisting system, like the columns and the beam, which is have two elements here, and the shear wall. Okay, and here the diaphragm. So the building in physical shape system, structural system, we have wall, we have column, we have beam, we have the diaphragm, and we have the foundation. The foundation can be isolated, can be combined, can be raft, depend on also the soil type, depend on the area or the land of the building that need to be constructed. So this is a substruction design. Okay. So, okay. Now we need to simplify the structure system. How to simplify this one? The simplified structure system. Sorry. We have the structure. Okay. This structure beam is supported by columns. Okay. It's supposedly to be excited, okay, from loads. These loads can be vibration, settlement, thermal changes, excitation loads can be earthquake, can be wind load, and the structure will get this all the excitement, and there will be a response. So as action, reaction, with the response will be the displacement. Can be displacement, can be strain, can be stress. This is what we are going to simplify the structural system. The structural system from beam, column, diaphragm, foundation is one unit. This one unit is exposed by load, and this load have a reaction is to find the displacement, the strain, the stresses, deformation, bending, moment, shear, stress, all related to strain and stresses and displacement. Okay, the finite element method, ETABS, considered as a finite element platform. The finite element methods is a numerical procedure for solving differential equations associated with the field problem with an accuracy accepted to the engineers. This is the partial differential equation with I think you are familiar with. Each particular element has a plane x, y, y, z, z, which is under equilibrium. Okay, so from the classical to finite element solution, which you should see that from the partial differential equation, we go through the principal virtual work through this structural model finite element. I'm explaining this. I don't want you to only use a model like a gaming or video game. No, I'm trying to explain this to know how we develop, how the engineers, how the researchers use these differential equations to use it in a model into finite element for more simplification for the engineers in design, not going to manual design. So this is the process: partial differential equation, going to virtual work. Then the virtual work, you are going to find the stiffness displacement force. Remember the spring was that you pull and you can get the response displacement. Okay, like this. This is the load, pushing, deforming. The same here. Pushing, the stiffness of the building, and there's the response of the building, which is the response is a strain. The strain is the delta L over L, which is the deformation over the full length. F equal KT. Okay. Basic steps in finite element analysis. Starting evaluating real structure. Okay, bringing a real structure. From this real structure, you are going to create the structural model. But you need the data of the real structure, right? You need the architecture plan. This architecture plan should be converted into structure. And from this structure plan, it can be converted into model. From the modeling, you are using discretized model in finite element. So the first two stages is classified for engineers. The third stage is a finite element and engineer. Okay, now when you input to the model into the finite element, it is now the finite element turn or finite element responsibility to solve the model based on what we say. This solving a finite element model, it will be based on what we explained before. What we explained before about this. This is the actual structure, partial differential equation, virtual work, we have the response. So this modeling in quick and fast analysis, how the generation changed, or how the evolution changed from the manual design for the engineers in the previous time into using the softwares, much faster and more accurate. But it is also tricky. Using finite element is also tricky. If you don't know what to input, maybe we'll get a wrong result. So be careful. After this, the engineer need to interpret the analysis. Okay, you interpret the analysis, and finally, okay, get the result, physical significance of results engineer. So the beginning start with engineers, at the end finished by engineers. So this is how the basic steps in finite element analysis. Okay, let me show you how to describe the following. As we say, we can take a particular element. This element can be a solid element, have an x z y plan, x z plan, and x y plan. If we take one particular element like this, it can represent it as a column element and can be represented to beam element, and can be represented as a floor element. So from this quantium discretization, we can see how this particular element study can be converted or can be explained into column, beam, and floor. Okay, the column, we have it, okay. The beam, we have it. The floor, we have three types, which is membrane, we have plate, we have shell. We can see the difference. The membrane can resist only the inner plane deformation shape. The plate or the slab can resist only the outer plane of the floor. However, the shell, both inner plane and outer plane. Sorry. So now we are going to see what type of analysis should be carried out. The type of analysis is to be carried out depends on the structural system, the type of excitations, the type of structure, the type of response. So to know which analysis you are going to use, you should know, okay, this building, is it important to be designed for earthquake? You should ask your question. If yes, okay, what type of analysis I should use? Okay, this building, is it necessary to be designed for wind load, for example? Depend on the location, for example. If yes, please go do it for the wind load. Does this building also necessary to be designed for gravity load and wind load and earthquake load? With these all combinations, please go and do it. So also, not only for the type of excitation, okay, type of structure, the material and geometry. You know, we have several types of letter resisting element. We have different type of structural systems, different type of material, and different type of regularity and irregularity in the geometry of the structure or of the building. For example, if you are particularly talking about the building. So the material, timber, different than steel, different than concrete, different than masonry, in a lot of physical and mechanical properties. Similar for the geometry. So the type of analysis to be selected is important to know what type of structure you are going to use. So the first two main points, type of excitation and type of structures, should be considered when you are going to do the analysis. Okay, the type of response. Okay, what response you are going to see? Stress, strain, displacement, drift, deformation, settlement. You need to see the deformation shape for the floor. Okay, deformation of the shape of the floor comes from the gravity load, right? So type of response is different. Okay, you need to see the deformation of the swaying of the building under wind load. Okay, you should go to the wind load direction, horizontal direction, and see the drift of the building. You want to see the torsion, the torque of the building, the twist of the building. You need to see the center of mass and center of rigidity of the building. So these three types or three conditions are necessary to be considered in the engineers. For the engineers or any designer should take into consideration these three types. Please, this is so important to consider this. Okay, now the structural system. Again, the simplification of the structural system. We go from static. The excitation can be static. It can be dynamic. Okay, this building will be excited under static load or dynamic load, and this structure will have a behavior elastic or inelastic, linear or nonlinear. See how we try to convert all this building in this starting point and ending point. Static, elastic, linear, dynamic, inelastic, nonlinear. So static, dynamic, elastic, inelastic, linear, nonlinear. Okay, let me show you how the basic analysis types is going. Excitation, the excitation, static and dynamic. We have 1, 2, 3, 4 static. We have 1, 2, 3, 4 dynamic. We have elastic, inelastic. Okay, we have linear, we have nonlinear. So maybe you will find the response is linear elastic. Okay, it can be linear elastic, can be nonlinear elastic, can be linear inelastic, it can be nonlinear inelastic. So this is a combination. It's a combination. You can make it like static. Let me draw a row for you. Static can be like this, inelastic, and can be linear. Also, the dynamic can be elastic and can be nonlinear. So it's like a combination. Okay, it can be static, elastic, nonlinear. It can be dynamic, inelastic, linear. So this is how I want to explain. Undo. Okay, let me undo this. This. Okay. Okay. So So this is the basic analysis type and the combination. So the static definition, when the excitation load does not vary with respect to time. Simple definition. Also, when the load can be assumed to be applied slowly. This is the definition of static. No variation with respect to time. On the contrary, on the other hand, the dynamic excitation is it varies with respect to time. For example, the earthquake or the ground motion records. The ground motion record, it is like a relation. The ground motion record is like a relation. This is, for example, the record. This, let me try to draw something like this. Okay, this is the ground motion. Okay, okay, let me try to see this. This is, for example, the time. This is the peak ground acceleration. Okay, so with respect to time, the response is changed. See, this one. This is the ground motion. Okay, this is the ground motion. If you apply this earthquake, you will see the response of the building is also changed. It's also changed. So this could be the time. This could be, for example, displacement. For example, at time 0.2 seconds. Okay, for example, this 0.2 second. I found the displacement 0.4 mm, for example. By time, it changed. By time. So here we are going to say the excitation varies rapidly with respect to time. So the response also will be varies, will not be linearly increasing or linearly decreasing. So this is one of the example in the dynamic analysis. Let me remove all this. Okay. So again, note, most real excitation are dynamic, but are considered as quasi-static. Most dynamic excitation can be converted into equivalent static. This is true. We will show you this during the analysis, during the model, how to use this. Okay. Now, the elastic material is, as a definition, elastic material as a definition follows the same path during loading and unloading and returns to initial state of deformation, stress, etc. after removing of load and excitation. So the elastic during loading and unloading, it can return to initial state. There's a familiar familiar diagram, which is this one, sorry, this one, and this one. And I remember that, okay, this one. Okay. And let me draw this and like this, right? I remember this one is familiar for yielding. Here you are going for yielding. This stage, we call it elastic stage. We call this stage is linear stage. So when this one, when, for example, you give a steel rebar and put it under tension or tensile stress force, under tension, if, for example, the rebar is 420 megapascal yielding, if it reached before 420 megapascal and you release the loading, it will return to its zero initial pass. So this is the elastic range. This can be the plastic, and here's the rupture. I just want to highlight about this because I'm highlighting about the modeling, about this informations, because it is important. You as a designer or as going to model something, you should understand the basic concept of modeling, basic concept of structure, what is the action, what is the reaction, what is the response you need to do, what is the type of analysis you want, what type of structural, what structural system you have, what is the material, what is the geometry, all this combination, you should know it. So the elastic, as I explained, is during loading and unloading, it returns to initial stage. For the inelastic, it doesn't follow the same path, okay? It doesn't follow the same path. During loading and unloading, I may not return to initial state of deformation. It may not return to initial state of deformation, stress, strain, after removal of loading system. So after removal, as I say, after removal, it can return back, okay? After removal of loading, it will not return back. Here, after removal, it can return. So you know now the difference between elastic and inelastic. Most of the material exhibit both elastic and inelastic behavior depending upon the level of loading. Exactly. Based on the loading, most of material can be done. Now, the linearity is the response directly proportional to the excitation. Nonlinearity is a response not directly proportional. So the deflection can be double if the load is doubled. So if I put 100 kilonewton, for example, let me draw this building. Imagine this is a building. We have 2 floors. We have the support. I have the support here, okay, and I applied and I applied 100 kilonewton force, and it gave me the building was deformed. See, this is how to do this. Okay, the building will deformed in this stage like this. Okay, so the building will deformed in from here to here. The deformation will be, for example, 10 millimeter. So for under 100 kilonewton, it deformed 10 millimeter. So if I change this to 200 kilonewton, I will give deformation 20 millimeter. So this is the double that we are talking about, linearity. On the contrary, the nonlinearity, the deflection may become 4 times if load is doubled. So if the load is doubled, it doesn't necessary to the displacement is doubled. It can be 4, it can be 5, it can be less. This is nonlinear analysis. So I'm trying to simplify as much as I can each point in I'm explaining. Okay, so again, oh yeah, this is the linearity and nonlinearity in the statistic, elastic and linearity. We have the linear, elastic. We have linear. See, it's drop here. It is linear, right? But it is drop in the stage. So due to inelasticity, here we have non-linear, but still elastic. There's no dropping down. We are not reaching to the collapse stage or the rupture stage to drop down. Okay, and here is non-linear and inelastic. So I hope this is clear now, the linear and non-linear, because it's really important for you as engineers to know how the material behave, how it is also based not only for the whole structure, it's also for the material. If you get concrete sample, cement sample, mortar, if you get steel rebar, if you get fibers, you should know the material, how it's behave. It's not only for the structure. So now meshing, this is in the finite element. We have the meshing. In general, the mesh in the slab should match with the match in the wall to establish connection. This is connection. So usually this is a finite element analysis. Each node has 6 degrees of freedom, x, y, z in translation, and rotation r, x, r, y, r, z in the rotation. So we have 6 degrees of freedom. And from each node, you can see the stresses. When you analyze the system later, when you go to the shell of the slab, you will see this mesh. And you see this mesh. There should be a compatibility between a connection between the two systems, or between the shell element and the area element. Both are area element. And edge constraint here. Some software automatically establish connectivity by using constraint. As in ETABS, we have this option. So the diaphragm, this one is an example of the diaphragm behavior constraint. See all the vertical element will move together because we define the diaphragm as a rigid body, no any plane deformation. We have semi-rigid, we have any plane deformation, flexible, thin slab or slab with opening area. This later in the modeling, we usually use rigid. We usually use rigid because this is basically depend on the stiffness of the slab with respect to the stiffness of the vertical element. Okay, if the stiffness of the slab is less than the stiffness of the vertical element, it can be between the semi-rigid and the flexible rigid. So there's a lot of yeah, you can follow my research about this in my PhD. I used to explain this in details. So it's not our aim, but let's continue. But I want to highlight that the diaphragm, we have 3 types: rigid, semi-rigid, and flexibility. So also for the boundary condition for the support can be fixed, can be pin, can be roller, fixed, pin, roller. This one for the simple support for the buildings. Also for the elastic support, spring to represent the soil. Okay, this is the spring. We have also the spring like this. We have the spring like this for defining the soil structure interaction, and stiffness Z, stiffness Y, stiffness X, Y, Z. So the foundation modeling for pressure determining this load is permitted to consider the structure to be fixed at the base. Okay, type of lateral resisting system. So type of the lateral resisting system is about, need to define we have bearing wall system like this one. We have shear wall system. Like this is shear wall alone. This is a shear wall alone. We have diagonal bracing. We have moment resisting frame resisting, can be special, can be intermediate, can be ordinary. This is based on the response reduction factor, R, which is ductility level, depend on the standard code you are following. For example, ACI code, they use R as they use R as response modification factor for in ACI code. They use this one. Okay, and in Eurocode ECA they use using behavior factor Q, and as I say, ACI code to use response modification factor R, and both of them related to ductility level. Okay, so this one is based on the connectivity between beam and column connections to be special for existing earthquake, to be intermediate, can be normal, ordinary. So just for information. And dual system, we have shear wall and we have frame. So the resisting system for the shear wall, this one for the shear wall can carry gravity load as well as resisting load, lateral load. Behave as vertical cantilever. Imagine this is the cantilever deformed. Take the fracture shape of the cantilever and it's deformed. If T greater than 5B shear wall, if T less than 5B column, this one is based on ASCE code. Okay, I don't know what is in India they use, but I'm familiar with ACI, Eurocode. So the American and the European code I'm familiar with. So type of shear wall geometry, how to consider it as a short, squat, cantilever. So depend on the height and depth, height and depth. So the flexural failure here, we have the flexural failure, we have horizontal shear failure, we have vertical shear failure. So the shear failure, shear deformation failure is dominant in short and squat walls. Bending deformation. This is not I can't follow this one, but mostly deformation failure is dominant in the short. I'm not sure about the squat, but yeah, about mostly short. So this is the detailing in the resisting structure system. Usually you put boundary element at the left and right of the shear wall. Just like this is a shear diagram, this is a bending diagram. Similarly for the moment resisting frame. This is like a brief just to remind you how many structure system we have. We have dual system, we have moment resisting system, we have shear wall system, we have bearing system. So we have a combination of bracing system. So both of this structure system are, you should put in mind that you should know how to model and how to design this later on. Okay, so now for the center of mass and center of rigidity is also really important. What is the difference? You can see the based on the two figure here. You see all the columns in the same direction. Okay, similarly here all columns same direction, but the beams, there's no beam here, there's no beam here, there's a beam here, there's a beam here, there's a symmetry. So the CM and CR can be compatible to each other, but the CM is away from CR. For example, if the CR is here, there will be an eccentricity E, which may affect a torsion, which will make a torsion. So this also I want to highlight about it. It's really important for me or for the engineer to know, and never neglect the torsion effects on the building. Okay. Now, what affects education center of mass? Why need to define center of mass? So this are too many questions. Well, similarly, center of rigidity of shear wall, see the symmetric, the shear walls in y direction, the shear wall in the upward y direction. So the building is stiff in this direction. If you split this core, if you split it into three walls, wall number 1, wall number 2, wall number 3, we have 2 in x direction and 1 in y direction. So in which direction is much stiffer, this building? Okay, we have 1, 2, 3, 4, 5 in x direction, and we have 1, 2 in y direction. So in the 5 direction is more resistive more than the x direction. Here it is only we have 2 shear wall and 1 core, and nothing is here. So center of rigidity and the stiffness and the inertia will consider the torsion effect here. Okay, so now distribution of the structure vertical element, same. Here COM equals COR. Why? Everything is symmetry, everything is same. No torsion. Here, as I say, there's torsion here. There's a torsion. So center of mass, center of rigidity, because it's clearly you can see that the stiffness of the two walls is different from these two columns, or this is like a wall, this is like a columns. So basically it will rotate. So this is how to know true, correct, wrong, no, correct, wrong. So this one is y in y direction. This one in y direction, very stiff. This one in x direction. This one in x direction. This one in y direction. This one in x direction. This one is stiffer. In this case, see, we have equilibrium, or not equilibrium. You can see this one is resisting in x direction, and this one is resisting in x direction, and this one is resisting in y direction, and this one is resisting in y direction. So this is a past scenario. This is the past scenario. So what is the dynamic properties of the structure? The dynamic properties of the structure is period, frequency, mode of shape, mode of vibration, mass, stiffness. So for each building, have a period T, which is equal T in second, and frequency F in hertz. And we have mode of shapes and mode of vibration, and we have mass and we have stiffness. Mode of shape can be different, first mode, secondly, third mode, so etc. So we have too many modes shape, like here what we can see, this mode number 1, mode number 2, mode number 3, 4, 5, 6. It can be for 12 and more and more. So a model analysis using ETABS eigen arrays. Okay, so this is the dynamic properties that we should know. Let me stop this first. Okay. So this is the description. It's mostly I talk about the modeling, not modeling, about the analysis concept. Basically, I talk about the base analysis concept and the building structure system as a physical behavior. So this is my this is what I want to explain first. Okay, so let's go now for ETABS. How let me explain to you. Let me share this with you. Let me share. Yeah, ETABS. Okay. Okay. This one is ETABS, as I explained before, is one of the commonly used program for analysis to design building, which is made of for the purpose of design. So what I want to show here. Okay. So this is the title bar. This is the title bar. We call it ETABS. This is ETABS version 18. This is ETABS version 18. Now the idea is of using ETABS is going to model. I want to explain first the interface of the ETABS version 18. So the idea of using it is going to model structures that have a structure. When I say model a structure, there should be an architect plan, which is the location of column, the type of floor system, the loading. If you have them, if you have all of them, all the architecture plan, you need to bring it to ETABS to model the structure. So the modeling the structure is the first part Following the defining material, assigning the load. After modeling, then you will go to analyze the structure. You have it. Then followed by design based on the standard code, and then detailing. So the process is modeling. So the process is modeling. Listen. Defining, assigning, analyzing, and detailing. So we have to know this: the modeling, defining, assigning, analyzing, and detailing is the process that we are going to use. So when okay. So this is the ETABS version 18. We have here the information on the latest news that come from any update from ETABS. See, we have CSI Revit Safe, CSI Bridge. This Safe is so important for the foundation and the slab design. And we have CSI Bridge. So this is the platform, or this is the box that is particularly explained the latest product release or latest news. From here, also from this side, we have a particular model. How to define the new model. In this box, how to define the new model. If you want to open ETABS and you have a project, go to new model. If you have this option is for opening existing model. If you have a model that you have done before and you need to continue, so you use opening existing model. And in this particular box, we have the recent model. For me, I have two buildings here. One related to hospital building in Malaysia and the other related to school building in Malaysia. So we have two particular buildings here. I have recently worked on it. Okay, we have now here, we have, sorry, stop this. We have to show you, this is the title bar. We have this one, we call it the menu bar. This one called the standard toolbar. And this one, we call it the quick drawing bar. So this one is the same, what is in the menu bar is same as the standard bar. So now it is inactive. Now it is inactive. When you press to new model, it will be inactive. So we should know. I'm explaining now the interface. We should know the interface of the software before we are going to the software inside, right? So if you press here file, you find a new model, right? Which is there. When I say everything in the standard bar is like a quick standard tool, you have it in this line, this bar. So file, I have a new model. Okay, where's the new model? It's this new model. Okay, file, open. You can see this one open. Similar file, save. This save, but which is inactive. So and you can use new model from here. You can use new model from here. You can use new model from here. Whatever you want. You can import any model from outside. We have Revit structure. If you have any model in Revit, any file from Revit, you can import. If you have the XF file, which is related to AutoCAD Architect, you can insert. If you have IFC file, also the IFC file is related to Revit structure or Revit software, you can use it. Also for the thread and the strut. So this is the interface of the ETABS. Okay, let's go now to the, let's press new model. You can press from here, you can press from here, you can press from here, whatever you want. I'll press from here. In the new model, we'll go to, you start the new model. Okay, first initialize the model. The model, which is first initialize the model. The model have settings. we have use the built-in setting. When you go to the model, use built-in setting. Yes, sorry, I want to highlight about something. That this ETABS is not the latest version. There's now ETABS version 19, if I'm not mistaken. But this one is okay. This one is good. Not a big difference between the new one. Of course, there's additional tools and options it can be added in ETABS 19, but this one is okay. You can learn and you can use it. So what setting? Well, before you initialize the model, you should go to the setting. You have US customer, you have metric, use metric. Now the ETABS have a steel section database. The steel section database, we have a lot of database here. This one related for the American, this one for Australian and New Zealand database section, this one for the Chinese, if not mistaken, this one for the Canadian, this one for the European, Euro, Indian, Korean, Russian, Nordic. So we have a plenty, also British. We have a plenty of section steel details based on what the product that you have in India or what I have now in Lebanon or in Malaysia. Yeah, by the way, it depend what's the product that you have in your country, what type of section you have. You can select the steel section database or the steel section type that you have. Okay, what is the steel design code? We have a lot of codes here. American codes 360, which is version 2016, if you want to read this. Also, this one is AISCE is American 360 version 10 or 2010, 2005, LRFD 93. So see how it's the version changes. And here's the CSA for the Canada. This is for British Standard 2000. Eurocode 3 2005. You know, the Eurocode have eight books. Eurocode 1, 2, 3, 4, 5, 6, 7, 8. EC1, EC2, EC3 like abbreviation. Now Eurocode 3 for the steel. IS is for Indian Standard, Italian, Korean, New Zealand, and Singapore. So, and also not only for the steel, we have the concrete design code. The concrete design code similarly, ACI code, the American code. We have version 14. See, version 14. I think now the Americans they have the latest one, which is version 19. So, but also we can use the ACI code 14 because they are giving you option to use 11, 2011. When I say 11, 2011, 08, 2008, 14, 2014. So this is the year. And for the concrete for Eurocode 2, it's 2004. And it says so. Initializing the model based on what is the project that you have. Okay, I have the project. I use the metric, no problem. The project is steel or concrete. Ask yourself. Okay, steel. If it's steel, what sections in that the country have in the database? What type of sections they have and the materials they use? You can select what code you are following, with what standard requirement you are following. If you are in India, you use IS, I think. Concrete design, similarly IS here for India, or so you have too many options to develop this one. After this, you can go to when you settle, when you put all the settings, you please press OK. Okay, and when you open, now we have the template, new model quick template. We have several options here. We have 3 boxes. If you can focus, notice, draw box. We have the grid dimension box. We have the story dimension box. We have the structure objects. So what is the difference between these three types? The first box, the first box can be split into two, 1 and 2. The grid dimension is usually used for the uniform building or for the regular building. We have number of grid in X direction, number of grid in Y direction. So this system, this grid dimension is only for regular building, which is I think is rarely we have a building is regular. And the second option is custom grid system, which is for irregular buildings and also can be regular. You can use this one, and you can use this one only for regular building and this one for irregular buildings. However, in the story dimensions, similarly, we have to separate this to two. This one for regular and this one for irregular. So again, and remove this. So if you go to for the regular grid label, you have to show this. If I have 4 in X direction, I have 4 in Y direction, and the spacing is 8 by 8. So you can change. If I have 4.5, I cannot change my 4.5. It should be similar. 4.5 in X direction, which is uniform. I can make this 6 in Y direction, but I have number of grid line is Y in Y direction is 4. So as to draw the grid, let me show you. Let me show you, for example, number of grid 4, number of spacing in X is 4.5, and this one is 6. I will press OK. I want to show you what will happen. See, you can see here in the plan view. Sorry, I want to explain this later. See, in X direction, 1, 2, 3, 4 grid line, 1, 2, 3, 4 grid line, 6 meter, 6 meter, 4.5, 4.5. So this one for the grid. Let me return back. Let me make a new model. Okay, a new model again. Let me make use build metric, for example, section. Okay, use ACI code. Okay, now this is for the uniform. If I want to use also for the uniform, again, let me show you again. This is for uniform building. Let's have 4 grid line. Similarly, 3 by 6. Okay. Let me show you the number of stories. For example, 10 stories. The typical story height, 3.5. I can make the bottom story height 3. This one for the regular. So I have 10 stories with 3.5 story height, with bottom story 3. We have 4 in X, 4 in Y, 3 meter spacing in X, 6 meter spacing in Y. And it is the grid option. I press OK. So I have now 1, 2, 3, 4, 1, 2, 3, 4, 3 meter in X. You can see the global axis here, X. Similar for here, you can see X, Y, and Z. So X in X, Y in Y, 3 meter, 3 meter, 6 meter, 6 meter, 6 meter. You can see here we have 10. Okay, let me tick for you. Let me tick. This could be number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stories. Each story is, as we say, 3.5 meter. 3.5 meter. So just to show you. So let me remove this. So this one, how to for using regular building, okay, regular, this one is regular, and in the grid system. Okay, now let me go for the irregular building. New model again. I'm always going outside and inside just to explain the interface of the software. So metric again, SCI. Now for if I'm going to use the grid system for irregular, I have entity grid system. For example, I have A, B, C, and D. And I have here 1, 2, 3, 4. You can see this A, B, C, and D in the x-grid direction. And I have 1, 2, 3, 4, 1, 2, 3, 4 in the y-grid direction. So if I want to change it, I can change this one to 4. See, it's changed here to 4. You can see this. It's changed here to 4. Let me show you. Okay, this one it changed. So 0, 4. This is the spacing. So I want to give this one 10. See, this is change here. I want to give this one 12. See, 0, 4, 10, 12. So from 0 to 4, you have 4 meters from A to B. From 4 to 10, you have 6 meters. 10 minus 4, you have 6 meters spacing. We are talking about spacing. If you go from C to D, from 10 to 12, we have 10 to 12, the spacing also 2 meters. So let me change this to make it more convenient for us to see. Okay, it's 4 meters. So we have 4 meters at the beginning. I have 4 meters at the right side. I have 10 meters, 6 meters in the bottom. So that's how you can change and the structural system on the grid system for the irregular building. Similar for the y direction. Okay, 0, 8, 16, 24. Change this one to 3.5. Okay, 3.5. I can change to 7. I can just want to 4.5. So see how it's changed. So this one is so big. So let's make it 5. Okay. So this is how to change. So this is the behavior. 3.5 to 5.5. I have. Okay. I have this one 3.5 to 8. We have 4.4 meter and a half. And from 8 to 4.5, we have 3.5 and a half. So I can change this one to 6 to make it irregular. So this is how the way. You have here the bubble size. I usually leave it as because they are now intervening or crossing each other. So maybe you can make it less. You can change this one to 500. So 800. So for me to make it so we know 100 now, no. So that doesn't matter for this one. It's okay. It's okay. So okay, we change this. Remember, we change this. Okay, remember I want to change this to 6-story. No, we don't use this one. See, this for regular. Go to irregular. We have 6-story. You can right click, keep. We have a story 1, story 7. So from story 1 to story 7, you can change the name. For example, I will change this basement. Okay, change this to ground floor. Change this to mezzanine. Change this to first floor, second floor, third floor, and roof. So in this case, you can change. I can change this one. Usually the basement, I will make it 4.5 meters. Okay. The ground floor, I make it 2.8. The mezzanine, I make it 2.8. Sorry, this can be 3.2. And the first floor to 3.5, 3.5, 3.5, and the roof 3.5. So we have overall, the elevation is, we have 24.2 meters. So later I'll explain about this element master story. I'll explain to this later. So, okay, so we have now 1, 2, 3, 4, 5, 6, 7 stories with different, press OK. So see, everything is changed. 4, 6, 4 to 2.5, 3.5. You can see the name, third floor, second floor. The name is changed here. First floor, mezzanine, ground floor, basement. So this is the name of the floor. This box is for the plan view. This one is for the 3D view. This one for the model explorer, which anything you want in this project, you can go and check everything you want, structural layout, properties, structural object groups. So now we can see before, this is the title bar, we see. Now everything is active. The quick standard tool is active. The drawing tool bar is active. So everything now is active. And you know, now we have three platforms, oh sorry, you can see 3 windows, 3D, plan, and model explorer. So if I want to define one by one, this one could be, let me remove this one. Okay. This one, can be new model. This one for the file. This one for the save, redo, undo. This one to draw by pen. This follows the running analysis. Later on, when you press run, you lock and unlock, zoom in, zoom out. This one's a hand that you use to move on. You press 3D. This one, plan for this one, elevation. Now I will show it. This one also to, from perspective, different perspective view. You can see this one to change between up and top and bottom of the, from, if you want to change from story to story. So I will explain in detail. This one for the design, this one for the analysis. When you run analysis, now it's inactive. When you have the analysis, you can use it. And similarly here for the drawing bar, we have a lot of drawing bar. We have different elements to use. Later on, when you are going to model, I'll explain out this. So undo, remove all this. What is this? So now we have, you can press this one. See how it moves. When you click on this, the light blue, so you are working here. So you are working here. When you press on this, now it's light blue. You are working in this area. So now we have 3D and 2D. You can see the elevation view. Press on this. This one shows the set elevation view. Which view you have? You have A, B, C, D. A, B, C, and D. We have 1, 2, oh sorry, 3, 4, 2, 1. So if I want, for example, A, press A. See? When I press A, now I can see the elevation view from the YZ plan. YZ from here. This is Y, and this is Z. When I press on A, press on B, you can go, you can shift by this one from A to B. So now we are seeing which part? We are seeing this part, this plan. we are seeing this box from YZ plane. Okay, now go to this one for one, press one. Okay, now it's different. One we are showing from XZ plan. We are now we are seeing sorry, again draw. We are seeing this one, this plan, this view. Okay, we are seeing this view. So now we know how the elevation, we know the 3D plan, we know okay, change this, close this. So we know how to shift from elevation 1, pressing this, elevation 1, pressing this, elevation view 2, 3, 4, etc. So now we know the interface of the ETABS. Okay, let me show you now. Now we show you the grid system, how to know the regular and irregular building in the grid system. No, again metric. Okay, now we have that. We know this one. Now we have different type of structural system. Remember when I told you that we have different type of structural system? We have steel deck, truss, flat slab with perimeter, beams, wafer slab, two-way or ribbed slab. So if you go for flat slab, for example, okay, press flat slab. We have the flat slab dimensions. You want drop panel or not? The size of drop panel should be 3 by 3. The left edge of the distance. The flat slab will be located. The flat slab will be 0.3 meter along x-axis. I will show you what does this mean. Okay, we have a slab. You can change. You can define everything. We have slab 1. Later, I will explain to this dead load and the live load type of rigid. So, okay, flat slab 0.3. Okay, we deal with this. Okay, we deal with this. You have to use a custom grid. Okay, use a custom grid. We have 4 stories, 3 stories, 4 stories, 3 meter typical height, 3 meter bottom strip, flat slab. Remember 0.3, 0.3, 0.3, 0.3, and drop panel 3. Press OK, and this one. See, we have 4 by 4. When I say 0.3 from the edge, what does that mean? That means this one. This one, the distance from here. This one. This one. From here to here. From here to here is 0.3 meter. From here to here is 0.3 meter. Okay. So that's why what I meant by the 0.3 meter for the edges. Okay, so we just want to explain this for you, how to know the spacing from the column to the edge of the slab. When I say the drop panel 3 meter by 3 meter means 3 meter from here to here, 3 meter from here to here. This is the square size. And don't look about this. Later we can explain this. This is a strip that we are going to use. And yeah, so this is how to model a flat slab with a drop panel. And we have 3 stories, 1, 2, 3. Each story is different height. Story number 4 is 12 meters. Story number 3 is 9 meters. Story number 2 is 6 meters, and story number 1 is 3 meters. So we have, in total, we have 4 stories. Now we have done this for the flat slab. Again, let's make a new model. Hopefully everything is clear. I know I have trying to explain in details and talk a lot, but I should give it in details to you to know how it's going. So again, we have different types slab. Flat slab with parameter beams. Flat slab, and we have waffle slab, or we can say two-way ribbed slab. Flat slab. So we have different categories here. Let me show you the flat slab without drop panel. Just remove the drop panel. Just turn it off, or you can change this to 0.5. No, 0.5, 0.5, 0.5, 5. So without drop panel and press OK. The same dimensions, 4 stories, 3 meter height, 4 by 4. Press OK. See, now we have no drop panel, and the distance now is more than 0.3. Now it's 0.5. So let me now show you this. So this is for the modeling technique until now. Not the modeling, it's only for the interface and how to use the grid system and etc. So let me go to something else. Something which is related to new model again. Yeah, before I forget, the unit is important here. You can change the unit from here. Metric, US, metric, consistent show unit form. You can see here's the list of units. Okay, we can see the structural area in meter squared, the angles in degree, the length dimension in millimeter, the section dimension, displacement, forces. You can change the unit based on what do you want, what actually you want. You can change, for example, here the modulus is megapascal, Newton millimeter. You can change this to kilonewton. I use a metric. I use metric. I have never changed this. No need to change this. Maybe I can change on the sections. Sometimes I use centimeter, sometimes I use meter, based on what is the architect plan that I have, based on how it's complete, the complexity of the architect plan and the dimensions. So I leave the unit as it is. So I would take now just break for a while. I'll break for a while and return back to you. Okay, we'll come back again. Okay, so recently we were talking about the grid system, how to develop a model or not a model, how to see the interface of the ETABS, how to know each bar function. This is we say ETABS title. Here's a menu bar, which is active now. This is a quick standard toolbar. Here's a drawing bar. So this is for the 2D plan view, and it could be for elevation as well. You see elevation AB, ABCD. You can see in A, B, C, D, we have 1 column, 2, 3, 4 column. From this side, okay, so elevation A, you can move forward to elevation B, from left to right, okay, from left to right. So here elevation C, okay, so we can change from to 1. So each elevation have its global axis, XZ, 1, XZ, this one. And if you go to this one, it will be YZ. So this side. So, and for the plan view, okay, for the plan view, okay, this is a plan view. The plan view is XY. Store number 4, we are here, store number 4. Z means the elevation, the height of the building, or go to store number 3. It would be 9 meters. Store number 2, 6 meters. Store number 1, 3 meter. Base, so 0 meter. So this is the particular block for the plan view. This one for the 3D view. Okay, so and recently we say that we need to check the unit. Use metric unit, or you can show the unit here for everything you want. Dimension, displacement, forces, stresses, stiffness, mass and weight, model factors, etc. So let me make a very quick brief now for what we have done today or for this video. Okay, first of all, we know the interface. We check the setting metric, which database section you are going. If you have steel project, which design standard code you need to follow. If you have concrete design, which standard code you have. Okay, I will follow now the American, SCI, AIC, and the metric. We'll have the thesis 3 block as a brief. This block number 1, block number 2, and multi-option here, block number 3. As we say, this one for regular buildings, this one for regular stories. Okay, and this one for irregular. So just to brief, I want to remind you of this, and here's your options. Okay, so this is a grid. This is a steel deck, and this is a truss, flat slab with perimeter beams. You can press on this option. You can see drop panel. Yes, okay. You want drop panel? You can use restraint at bottom. What type of boundary condition you need to use? Pin or fixed pin connection or hinge connection, which is constraint in translation X and Y, and here X, Y, Z, restraint. And here the structure system, column, beam, slab, drop. You can change the section of each model alone. This one will explain it later when we have specific model. And here type of dead load, live load in kilopascal, which are kilonewton per square meter. And the size can you change. So this one, if you want to see the flat slab with perimeter beams, you can see it now. Okay. New model. Okay. Slab. Parameter 4. Okay, now we have the flat slab. This is the slab. This is the drop panel under the columns, and this in the blue are the beams at the edge of the building, which is distributed along the height of the building. So this is another type of other option. If you want, if you have structural system like this, you can follow this one. Okay. And let me open a new the last option maybe. What's the last option? Okay, the waffle slab, which is this waffle slab. This is very famous one. You can see it. You can see the waffle slab. Okay. So this can be waffle slab model. So based on what you have, what building you have, what type of structure, you can use this one directly, and you can change the dimension. If you have a regular building, if you have a regular building, you go to this one. You can select how many stores you want. You can go to custom storage change. Okay. Also, for this blank, the blank, if you press a blank, to give you like a whiteboard with the horizon. This is blue horizon and nothing. Okay. But you can, if you want, if you don't have any specific structure system, you can go direct to grid only. And from the grid only, you can change, right click, press right click, add modify grid. Okay. Modify, we have add new grid system. You can change the grid system from here. You can change number of line. You can choose number of an X and Y spacing. So this is another grid system you can change. You have modify number of stories. You can go to modification, add a story, and keep existing height. For example, you want it above story 4. Okay, above story 4. Now you'll have story number 5. So this is another option in ETABS. If you need to do any modification on the structure, you want to add another option, another story, different height, you can go to grid directly, and inside the grid make modification and change the story height, and you can change or modify the grid system also from here if you want to make it irregular. So you can use grid, and you can decide regular one building or irregular building. From here, you can make it irregular building. And here you can stick on the regular building. So this is another option to show you. Okay, we still have to talk about this drawing bar. This drawing bar, if you see here, if you put your mouse on this icon, you will see draw beam column. So this icon for drawing beams and column. You can draw like this, like this, but of course, like this. So just move it. Want beam, you can draw from here to here. You can draw from here to here. You can draw here to here. So this is if you want to draw beam. This one, quick draw beam. If you have this, we'll talk about it later, not now. Okay. This one for drawing column in the plan view. This one to draw a secondary beam. This one, if you have bracing system, you can use a bracing system. This one for the floor area, for example, this one is the floor. I want to this panel. Okay, see, I have now floor here. So this is option to the floor. You want to delete this, just click delete. And here's for quick draw. Sometimes you need some options have quick draw like this one and like this one. And sometimes you can use this one also quick draw. This one for the drawing walls. If you have shear wall, you have core wall, you can draw. This one also for quick draw wall. And now opening in the walls and draw links. You can see the draw walls. You can have tendon if you have post-tension slab. This is the option. For example, get a previous selection. So I click this one, right? To select it. I want to remove it. Press escape, then press again PS. So it gives me the previous selection. Select all. You can select all. So yeah, this is for utilities. So this also, you can see down this comment bar. If you put your mouse in the grid point C3, this is C3. You can know the coordinate. Now we are in X equals 16 meter, Y 16 meter, and elevation 12 meters. So 16 meter, yes, true. 8 plus 8 equals 16. And in Y, 16 meter, 8 plus 8 equals 16. And Z equal 12 meter because we are staying on story number 4, which is 12 meter. So similarly, you can see this is the origin, 0, 0, 0. Let's go to the next one. You move in X direction, 8, 0, 0. Go upward, it would be 8, 0, 3, 8, 0, 6. Okay. So this is how to know the key features of ETABS. And that's all for this session. Hopefully you can please watch the video carefully, try to understand each step, and for any inquiries you can email me on my email. Okay, and I'll try to share this note. If you want anything, you can email me on this email. Thank you so much, and see you in the next video, inshallah.